Redox potential is a commonly applied measurement for inspecting chemical processes, industrial and municipal wastewater systems, and swimming pool monitoring equipment. This video explains the basic principles of redox potential measurement. Using the example of a combination electrode and a multi-channel device JUMO Aqueous Touch S, the video shows the startup of a measuring chain. The redox potential describes the tendency of substances to lose or gain electrons. For example, substance A gives electrons to a substance B. When a substance loses electrons, it oxidizes. A substance that gains electrons is reduced. The entire electron exchange process is known as redox reaction. The redox potential of substance A is more negative than that of substance B. The difference between the redox potentials is the driving force for the transfer of electrons. The redox potential known for numerous substances uses hydrogen as the reference system. Substance B takes electrons from substance A and oxidizes substance A, thereby acting as an oxidant. Substance B gains electrons and is therefore reduced. Examples for oxidants include oxygen, disinfectants such as chlorine or ozone, sulfur, or bleach. Substance A gives electrons to substance B and reduces substance B, thereby acting as a reducer. Substance A loses electrons and is therefore oxidized. Reducers include organic substances such as foodstuffs like sugar, fats and proteins, as well as base metals and nonmetals. The graphic shows the series of the metals with the indicated redox potential compared to hydrogen as the reference system. Metals with a smaller redox potential have the higher reduction potential. These metals give electrons to metals with the higher redox potential, thereby reducing them. Metals with a greater redox potential have the higher oxidation potential. These metals take electrons from metals with the lower redox potential, thereby oxidizing them. Taking chromium and platinum as an example, chromium has the greater reduction potential. Electrons are given to platinum, platinum is reduced, chromium is oxidized. As is also the case in the shown example, the difference between the redox potential is the driving force for the transfer of electrons. Generally speaking, every substance has a specific redox potential. If two liquids with dissimilar redox potential are mixed together, the measured redox potential infers the mixing ratio. Swimming pool water, for example, is chlorinated for disinfection purposes. The admissible concentration of free chlorine is 0.3 to 0.6 mg per liter. In this application, chlorine acts as the oxidant for organic pollutants. Clean water with the indicated chlorine concentration has a relatively high redox potential. If these pollutants enter the swimming pool water in increasingly higher concentrations, the redox potential falls. This means that the redox potential indicates the pollution index of the swimming pool water. Because the chlorine concentration in the application is set to a stable value, the redox potential is a parameter for organic pollutants. If the redox potential falls despite filtering, the filter system must be inspected. Highly toxic chromates occur in the wastewaters of electrolysis plants, pickling, etching, and chromating baths, as well as during the production of aluminum. The crucial elimination of these chromates from the wastewater occurs over several steps and is monitored by redox and pH value measurement. In practice, the wastewater is set to a pH value of between 2 and 2.5 by adding acid. Sulfide is used as a reducer. This effectively lowers the redox potential. For example, the redox potential is set to less than 250 mV. When the reducer is added, potential jumps over several hundred mV can be measured in a negative direction. During the detoxification process, the redox potential rises again. Over time, the reducer and the acid are depleted. Both are readjusted. The detoxification process is complete when no further potential jumps occur after the reducer is added. Finally, lye is added to neutralize the wastewater. Metal electrodes measure the redox potential of the measurement solution and consist of a glass or a plastic shaft. Located at the bottom end of the electrode is a metal piece. This piece is either platinum or gold due to the good resistance of these metals, even to aggressive chemicals. The combination with a reference electrode produces an entire measuring chain. The potassium chloride reference electrode is normally used in measurement technology. This electrode is better suited to industrial applications than the hydrogen electrode. The reference electrode has to deliver a constant potential, against which the redox potential of the measurement solution at the metal electrode is measured. The reference electrode consists of a glass or a plastic shaft and is filled with the reference electrolyte of a potassium chloride solution. The internal conduction system consists of silver-silver chloride. Reference electrolyte and conduction system form the reference system. The diaphragm in the shaft wall creates the conductive connection between the reference electrolyte and the measurement medium. The ceramic diaphragm shown is suitable for clean measurement media. As a rule, the sensor consists of a redox combination electrode, as opposed to two electrodes. This combination electrode comprises the metal and reference electrode components. The redox potential at the gold or platinum tip is moved along via the internal conduction system. Conduction system and reference electrolyte form the reference potential. The diaphragm creates the conductive connection between the measurement solution and the reference electrolyte. As an alternative to the ceramic diaphragm, the PTFE diaphragm creates the reliable connection between the measurement solution and the reference electrolysis in polluted media. Perforated or annular gap diaphragms are used for heavily polluted or adherent media. Signals are transferred between redox combination electrode and transmitter via a coaxial cable. The redox potential of the measurement solution is conducted through the inner core. The potential of the reference is conducted through the copper braid. Besides the redox combination electrode, a transmitter is also required for preparing the measurement signal. As an example, the multi-channel device JUMO Aquis Touch S permits the direct connection of up to 4 sensors via optional boards. The optional boards are available for the measurement parameters pH value, redox potential, as well as conductive and inductive conductivity. In the example, an optional board for redox potential or pH value is used for analysis input 1 or in 7. The electrode is connected as follows. The inner core is wired to terminal 1 of analysis input 1. The shielding is connected to terminal 3. Terminal 3 must be connected to terminal 5 via a short circuit jumper that is included in the scope of delivery. It is advisable to use the configuration program to configure the JUMO Aquis Touch S. Only a small number of changes are required to adapt the input for redox potential or pH measurement. The settings are therefore configured from the front of the device. Per default, log on takes place via the user master and the password 9200. The system is configured after the logon with this user ID. In the Aquis Touch S, the redox combination electrode is connected to analysis input 1. This is designated redox potential. The redox electrode must be selected from electrode type. The redox potential should be displayed in millivolt. The display range must be set. The maximal possible range is plus minus 1500 millivolt. No slope rate changes take place with redox electrodes. If a zero offset occurs, a 0-point calibration can be carried out. In the example, the JUMO buffer solution 475 mV is used as the reference solution. The calibration routine must be enabled. Besides numerous other display options, the Aquis Touch S offers 6 detailed screens. In the example, only detailed screen 1 is used. The detailed screen gets the caption Redox potential. The detailed screen can display 3 analog values: main value, secondary value and additional value, and 3 binary values. Detailed screen 1 should display the compensated value of analysis input 1. In the example, this is the redox potential in mV. No further variables should be displayed. These settings create the shown detailed screen. A calibration at the start of the measurement, as in the norm for pH measurements, is not required. The electrodes can be used immediately. If the measured value is reached slowly, the metal surface may well have passivated. This can be remedied by pre-treating the electrode surface. Notes to this effect are contained in DIN 38404 Part 6, for example. If the measured values shift, the 0-point calibration enabled beforehand can be carried out. As already mentioned, JUMO offers the redox potential test solution shown for calibration or testing the measuring chain. The solution is used for combination electrodes with a reference system from silver chloride. When using a combination electrode with an electrolyte from a 3 molar KCl solution, a redox potential of 468 mV occurs. If the combination electrode has a saturated KCl reference electrolyte, this is recognized by the salt rings in the reference system. A redox potential of 475 mV occurs. A 0-point calibration is carried out as follows. Once a stable value has occurred, click OK to confirm. The detailed screen displays the compensated redox potential. Thank you for your attention.